Concept unlearning in text-to-image models has become a standard tool for mitigating copyright, safety, and privacy risks. But almost every benchmark out there focuses on concepts that dominate the entire frame: artistic styles, broad object categories, or celebrity likenesses. There's a massive blind spot when it comes to localized, semantically entangled marks like corporate logos. A logo doesn't need to fill the image to trigger a protected concept. It can occupy just a few % of the frame, carry the entire brand identity, and be activated implicitly by context. Just prompting MacBook is often enough to hallucinate an Apple mark. Current unlearning methods treat this like any other global concept, and they systematically fail. Today, we're breaking down LU500, a new benchmark specifically designed to stress-test concept unlearning on Fortune Global 500 company logos, and why it exposes a fundamental local-global trade-off in modern diffusion architectures. Let's get into why logo unlearning is structurally different from standard concept removal. In diffusion models, concepts are typically entangled across the latent space. When you try to erase a broad concept like an oil painting style or a specific celebrity, you're suppressing a global distribution. A logo, however, is a highly localized visual signature. It requires precise typography, specific color palettes, and exact geometric proportions to be recognizable. If your unlearning intervention is too weak, you get residual strokes or blurred brand cues. If it's too strong, you destroy the surrounding scene, texture, and layout. This creates a narrow operating window. Furthermore, logos are contextually sticky. Modern T2I models have learned strong associations between products, storefronts, and their branding. So unlearning a logo isn't just keyword blocking. It requires spatially precise disentanglement in the latent space while preserving non-target content. That's exactly what LU500 is built to measure. LU500 contains nearly 10,000 curated text-image pairs, generated using Stable Diffusion 3 medium as the backbone. The dataset is split into 2 tracks to capture different failure modes. The explicit track, LUX500, directly names the target logo. The implicit track, LUM500, uses contextual prompts involving products, advertisements, or workplace scenes where the logo naturally appears without ever mentioning the word logo. This setup tests whether models can suppress brand leakage when the trigger is semantic rather than explicit. But here's where most benchmarks break down. They rely on binary success rates. Did the logo disappear? Yes or no? That's useless for localized edits. LU500 introduces a multi-grained evaluation protocol that separates local erasure from global preservation. For local analysis, they use ALV2, an open vocabulary detector, to isolate the logo region. Then they measure 3 metrics: clip score, which checks semantic alignment between the detected logo and the company name query; logo score, which measures latent clip feature similarity before and after unlearning; and logo SSIM, which tracks pixel-level structural disruption. For global preservation, they measure image score and image SSIM across the entire frame. The goal is to see if a method can zero out the local metrics without crashing the global ones. The authors tested this against representative inference time methods like NP, SLD, and Sega, as well as fine-tuning approaches like ESD and Forget-Me-Not. The results reveal a consistent and systemic trade-off. When you increase safety guidance or editing strength in methods like SLD and Sega, you do see marginal improvements in local logo disruption. But the cost is catastrophic degradation in global fidelity. Texture, layout, and object identity get warped. The intervention isn't localized. It bleeds across the entire latent representation. Fine-tuning methods show a similar tension. More disruptive weight edits reduce logo evidence but lower background fidelity, while conservative edits preserve the image at the risk of leaving brand traces. To isolate prompt-level mitigation from weight-level unlearning, they introduce ProLU, a multi-agent prompt rewriting baseline. ProLU uses a remover agent to strip explicit and implicit brand triggers, a reflector agent to stabilize the edit against overcorrection, and a checker agent for final validation. ProLU achieves the strongest local erasure scores because it removes the semantic triggers entirely. But it also changes the input description, which inevitably alters the generated scene. This is a crucial diagnostic result. Prompt filtering can mitigate surface-level leakage, but it does not solve localized model-level unlearning. If you want to remove a logo without changing the background, you need weight-level disentanglement, not just better prompting. To understand exactly when and why unlearning fails, the paper runs a correlation analysis between unlearning efficacy and intrinsic logo properties. They measure area, location, edge density, shape count, texture complexity, and fractal dimension. Most attributes show weak correlation with semantic scores, which makes sense because leakage depends on both visual form and prompt context. But logo SSIM reveals a clear signal. Larger logo regions are structurally harder to alter without visible damage, while high-frequency or complex regions are easier to disrupt. This points directly to a missing piece in current architectures. Global concept suppression isn't enough. Future methods need spatially aware controls, like SSIM-guided constraints or attention masking, that can target specific bounding boxes in the latent or pixel space while freezing surrounding regions. LU500 isn't just another benchmark. It's a diagnostic tool that forces us to confront the limitations of current unlearning pipelines. The data clearly shows that inference time guidance and standard fine-tuning methods are still too blunt for localized, semantically entangled concepts. Prompt space interventions help, but they're a band-aid, not a solution. The field needs to move towards spatially precise editing, latent masking, and structured disentanglement that respects the boundary between protected marks and legitimate scene content. If you're working on generative model safety, copyright compliance, or concept editing, LU500 should be on your radar. The full dataset, evaluation code, and detailed ablations are publicly available, and I'll leave links in the description. Thanks for watching, and I'll see you in the next one.